Hello, this will be your pre-lab webinar on distillation, which is the process we'll be learning Monday and is one of the most important lectures we'll have the entire term on any organic chemistry techniques that we'll be learning. And as I had mentioned earlier in the course, this first semester in the laboratory at least is primarily focused on you learning the different kinds of techniques that you use for separating items in organic chemistry, and also some work towards understanding some of the reactions. But they're pretty basic at this point, and they won't be very complex yet. Next semester, you'll study more about analytical techniques that involve destructive mechanisms of characterization and then some non-destructive mechanisms of characterization. But we don't focus as much on characterizing compounds in the first part. We focus more on separating them. And so that's kind of the biggest difference. And the other is there are more reactions next semester that get a little bit more complicated and ultimately that give people the most trouble, really. So we'll not dwell too much there, but what I do want to stress is that it's very important that you go through this lecture and learn this material, especially if you're in chemical engineering. This may be the first time that you're exposed to distilling compounds and this type of separation, and so it's a good introduction, and I've made sure to make it an introduction that will be useful for everybody depending on what they're going into. So if you're a chemist or chemical engineer, this is going to be a good presentation for you in terms of if you want to do anything, synthetic work, solvents, whatever it is you're doing. You'll learn how to separate them here, at least to the best of our ability to teach you. There are going to be some more advanced classes on this. Obviously, if you're in chemical engineering, you'll take more separation courses than everyone else will. So you'll learn better techniques for some of the things that I'm going to bring up. But a lot of it will kind of be the same and will kind of just be an adaptation of the same thing. All right. So we'll begin by looking at an overview of separation in general and kind of relate back to what we did last week and how that fits that model. And then we'll talk about distilling theories, and those will include simple distillations, fractional distillations, vacuum distillations, steam distillations, and then we'll talk briefly on what an azeotrope is and why that's relevant. And I'll give you a little bit of a glance into some future things that will help that make more sense. And then we'll talk about how to set up your apparatuses. We'll begin with separation theory. So the key thing with separation is that it's a multi-dimensional process when you look at it on paper. And it can be a multi-dimensional process in real life sometimes. But the key thing is you have to start with knowing what your mixture is. So you have a mixture. It's compounds. Some of them you want to separate from others. Some of them you want to purify. Some of them you may not care as much about purifying, but you still need to get them away from everything else. And we approached a problem like that last week when we talked about recrystallizing, because recrystallizing is in fact a type of separation. It is separating solids predominantly, because you're purifying a solid. This time we're going to talk about liquids. And so most of the time in chemistry, when we talk about distilling, we're talking about two compounds that are mixable with one another, that dissolve within one another, and that are both liquid. There will be situations where you can bubble gases through liquids to separate them, or even feed the gases through columns. We will not get into that in this course because we don't use any gases in the organic lab. as a feed or anything like that. We've just, it's not that we couldn't do it. We could do reactions where you looked at partial pressures and figured out how many moles of something you were putting into a reaction. And there are reactions where you can bubble gases through liquids and actually introduce chemical species into reactions. There are ways to do that and setups for it. And you have the glassware for it. But we just don't have any experiments where we do that. So the next thing is kind of what do you get into when you have liquids and gases? What are your options? And so, you know, between distilling, there's chromatography. And chromatography is, you know, pretty much only other method that you have for a liquid or a gas. Really liquids. Sometimes you can have solids in the liquids if they're dissolved and you're using the solvent as a carrier. But most of the time, we either recrystallize solids or we extract solids. And extraction is something I did not put on this table of, well, rather flowchart that I put together because it can go different ways. There's different kinds of extracting purposes. You know, first you have the liquid phases, and then you get the solid phases. And so it depends on what you're talking about doing. But the whole point of an extraction is using a reactive sort of solvent. And basically taking one compound that you know is going to be dissolved in the layer and making it more soluble in a non-miscible layer that can be separated due to density. And then you can do further work with that and you can retrieve the compound afterward. And there are reactions that use combinations of all these things, and you won't even think about it until you do it again. For instance, the Grignard reaction is a good example of that. There's a separation that occurs, and then after the separation there's a workup with acidification, and that acidification releases inorganic elements into an aqueous medium that may be or may not be soluble entirely, but that leaves you with an organic phase on the top that you can then extract and separate. So it will all be integrated together in some cases, and you have to do it step by step. Now, as to distillation itself, there are really four main types. You have simple, fractional, vacuum, and azeotropic. There is steam distillation as well. That could be a fifth topic, but steam distillation is not always predominantly used in labs. It's mainly for very special cases, and we'll talk about what those are. And then chromatography, you have mostly liquid chromatography when we talk about things that you're trying to separate with the liquids, or where you're trying to use a solid to dissolve in a liquid and then work it into a column to be eluted through. That can sometimes be done. That would normally happen in a gravity column. So you have gravity liquid chromatography, you have pressure liquid chromatography, you have thin layer chromatography. Thin layer chromatography uses an eluent just like the other chromatography examples here, except that it works on a small plate made out of oftentimes silica trapped in an aluminum matrix or in between glass pieces. So it's when we do TLC, you'll see what we're talking about with that, but it's a method of really helping see what will separate something in another chromatography setup, or you can use it to retrieve small amounts of compounds because you can retrieve them from the plate and then redissolve them and collect them. That's actually a lot more work than it's worth sometimes. Excuse me. Most of the time you want to develop a method that's a little bit more massive so you can do more at once. But oftentimes TLC can help you with the groundwork on that. There's a fly. But anyway. Alright, so gases. Now, you know, most of the time we don't use gas chromatography to separate gases, but you could separate with gas chromatography because gas chromatography itself is actually not destructive. There are some things that are destructive and there are some things that are not destructive. GCMS is destructive because GCMS is a characterizing method. You're taking a GC, hooking it to a mass spectrometer, and then you're running the sample through the mass spectrometer if you want to do that part. you can do that. You don't necessarily have to. You can just use the GC function on the instrument and measure the retention times, but it will also feed through the mass spec, and you can use the mass spec end of it. When you run something through a mass spec, though, you're destroying it because it ionizes the sample and it runs them through quadrupoles, and then you get mass charge ratios out of that, and then you can determine, you know, what kind of compounds you have based on fragmentation patterns. This is how a lot of instrumental techniques are done, particularly in protein work. MALDI-TOF is a type of mass spec oriented sort of analytical method where you're taking a protein sample and actually ionizing it with a laser on a special matrix. So you can take more courses on that, and you know, in biochemistry you'll talk a lot about chromatography techniques and different ways of separating things, and if you take analytical chemistry or instrumental analysis, you'll talk more about some of those things, and you might even use some of the instruments. If they have a lab or something like that, you may do some HPLC, which is high pressure liquid chromatography. Pressure chromatography methods can be a little bit more difficult to work with. It's not quite like a GC. You have to look at the pressure gradients and things like that when you're looking at how to calculate the retention times. And most of those setups, you have to run the experiment. You can't just set it up. You have to kind of run it and get some numbers so you know kind of what you're looking at for each specific case, because it's not always clear cut, and it kind of depends on the setup of your system and your solvents and different things. So we won't even get into that in this course. We'll never really teach you much about liquid chromatography or gravity columns or any of that. We just don't have time to do it. And quite frankly, we don't have experiments that we do that would benefit from it as much for you to learn from. So we tend to stick to really basic recrystallizing, distilling, things like that. And that's just, you know, the only reason I mention those things is just to give you an overview of what you can get into with organic. It's not to say that we don't do liquid chromatography when we work with synthetic molecules. We do a lot. It happens a lot. But we don't do it as much as biochemists do. It's just that that's kind of their work. You know, they may have to use those for proteins. And there's different kinds of columns too when you get into pressure chromatography. HPLC can be used with ion exchange, hydrophobicity, size exclusion stuff, affinity. There's a lot of things you can, you know, most of it's done at low pressure a lot of the time, but that doesn't mean high pressure is not necessary. Sometimes you have a column you need that for, so you have to have special setups for that and everything. And a lot of times the instrumental readings for your retention times are built into the instruments, so we just don't have that kind of setup here to really work with that with you. But we do have some GC results that we'll have you work through eventually, and that'll be coming up in a couple of experiments. We're not quite there yet. And so, not to get off track too much, we come back to what we're doing with it. And so, you know, once you go through those methods, hopefully you've gotten it separated or purified. If you do, you're done. If not, you have to go back to the starting point and rework your whole idea, because it may be that you have to use a different solvent system or some other kind of thing like that to get what you want. So we're going to move on to distillation. Simple distillation is ideal for certain circumstances. Basically, anything that you're using in a simple distillation, your boiling point is going to have to be less than 150 degrees Celsius at 1 atmosphere. We consider that to be a normal boiling point. It's just kind of a standard marker, because you'll remember from general chemistry the explanation that an item boils when its atmospheric pressure, well, it depends on how you're measuring pressure, but the vapor pressure of the liquid becomes equal to the atmospheric pressure over the liquid. Once that happens, an item boil, or a substance boils. So you basically want to look at that 1 atmosphere as that pressure at which everything is becoming equal to. And if that's the case, this boiling point is less than 150 degrees Celsius if you're using a simple distillation, but it's also got impurities that are not volatile. The liquids are dissolving in one another pretty well. They're not trying to separate, and there's at least a 25 degrees Celsius gap between each boiling point of each compound in the mixture. And that has to be the case because if you look at the temperature versus volume collected graph for a simple distillation, it generally tends to follow kind of a linear pattern. I'm not saying that it's completely linear. There are a lot of curves that will show a very, very slight sigmoidal kind of shape or even like a slight cubic shape, but it's very, very subtle, and it looks almost entirely linear most of the time. And so because of that, because you're constantly heating the sample and you're separating it, you're getting a mixture of all the compounds that are coming over at one time, and it's intermixed. It's not a perfect separation. And if you want something to be pretty pure with a simple distillation, it has to follow those rules because you need to be able to get the majority of each compound separate from one another. Otherwise, you're wasting energy trying to do the method to begin with, because it's not really going to separate anything to any kind of appreciable degree. Fractional distillation is the very special case that can do almost anything as long as the two compounds can dissolve in one another and aren't trying to separate on their own. The boiling point can be any value. It doesn't matter what it is at that 1 atmosphere. It doesn't have to be less than 150. It could be greater than 150. It could be whatever it is. There is some way to make a column for it generally. The BP, or boiling point in this case, not blood pressure, has to, it doesn't have to be 25 degrees Celsius apart. It can be very, very narrow. They could be 5 degrees apart. Hang on. They can be very narrow. They could be 5 degrees apart, 2 degrees apart, whatever amount of degrees apart. There's generally some way to work a column into it and get them eventually separated from one another. It would be pretty difficult if the boiling points are really, really close together, but it can still be done if you make the column tall enough. There's a lot of things that go into making fractional distillation work for a process, and we won't get into too much about what makes it better or worse, but we will talk about it a little bit so you understand why it's so different, because that's important. So the first thing I'll have you do is take a look at this graph that's over here on the side and compare it to the other that we just saw a moment ago for simple distillation. If you look at it, for the most part, the temperature of our mixture as it's being distilled is staying fairly constant as volume collects for that particular point or amount of time. And then all of a sudden, once the majority of that compound has been distilled over, there's a giant spike in the temperature here. It's a really drastic change, very vertical. And the reason for that is because of the theoretical plates that exist in fractional distillation. One compound tends to come across first and be purified and then drained off, and then another starts going into the vapor phase more and continues on, and the temperature stays pretty constant during that process. And you could keep going, and there'd be stair steps on stair steps of these different items coming out in the separation. So that is the advantage to fractional distillation. That's what makes it different from everything else we'll talk about. And we'll spend the majority of the time in this lecture talking about fractional distillation and why it works, because it's the most important one. Alright, So before we can really understand what's going on with theoretical plates and how they exist and how to find them and visualize them and this sort of thing, we have to understand just a little bit about some general chemistry equations we learned way back when. And I know some of you have probably forgotten some of them, or you may not even remember they were, because maybe the book they had didn't cover it as well as another, or maybe you took chemistry somewhere else and they didn't talk about it, or who knows, it might have been a while since you had general chemistry. Hard to say. But either way, it was talked about. All of these things were here. So, the first is the ideal gas law. And everybody should probably remember that much, that PV equals nRT. We have to use that when we consider certain explanations of what's going on in the column. The second is that Dalton's law of partial pressure governs how you sum partial pressures to get the total pressure of a system. So you have to remember that. And the shortest way to write that is the way I have it here. And for those whose math background may not be as strong as others, or who may have forgotten, or if you didn't know, this symbol, the sigma, with the I equals 1 over n, p sub I, says exactly that. It says I am taking the sum of all the numbers of data that I have for the partial pressure I in this system, and I'm adding it together and getting a total pressure. That's really all that says. Now, Réault's law is different. Réault was a French chemist who basically explained how partial pressure change works in a mixture. It has to be a mixture. It can't be just one compound. It has to be multiple compounds in a mixture. And what he says is that for the partial pressure of a particular compound, it will be equal to the mole fraction of that compound in the mixture multiplied by its pure vapor pressure at a given temperature, which is taken to be constant at that point in time. So, and basically what he's saying is that this pressure here is when the mole fraction is equal to 1 instead of some fractional part of 1. And you can substitute Réault into Dalton, and you get this simplified expression: total pressure is equal to the sum of the product x sub I times the pure vapor pressure at the particular selected temperature. Now, the problem with this setup is that in a distillation, the temperature is changing. It isn't constant. There's no way that it is. So you can't actually use these equations alone when you want to look at what's going on in the column. You just can't do that. You have to take into account temperature variation. And there's only one formula in all of chemistry that relates partial pressure to temperature change. And we're going to go over that next. And it's the Clausius-Clapeyron equation. So if you remembered from general chemistry, some general chemistry professors did talk about this briefly. Now, I know a lot of the books don't have this equation, and I know most of the professors did not have you do any problems with this equation. So I don't expect you to all entirely remember it, but you should be at least aware of it. And I don't expect you to do any calculations with it, because it's more of a physical chemistry thing that those of you who take physical chemistry will probably do in the second half of the course when they talk more about gas laws and thermodynamics and things like that. But it's a very important equation. And I'm going to kind of first go over the parts of it so we're not all confused on what we're looking at. So the P that you see here, okay, is the partial pressure at a given temperature. The P that you see over here with the superscript naught is the vapor pressure at the normal boiling point of 1 atmosphere of pressure. It's different from Rayoult's laws because Rayoult's law, the P of naught there is actually the P in the Clausius-Clapeyron equation. So that's the distinction between the two, and it will be a little confusing to follow because of that. The key difference here is that vapor pressure at the normal boiling point is multiplied by the exponential, and this here, for those who have not seen it before, means the number E raised to the power negative delta H over R times the product 1 over inverse T, the inverse of T minus the inverse of T naught. That's what that means. And the delta H that you see here, some of you, if you're taking thermo in chemical engineering, you will know it by a different variable name, which is L sub V. There's not always consistency between the different variables that are used in different texts and courses, and so I include this here so we're not all confused about what we're talking about, because I didn't put a VAP here. Technically, I should put a VAP here in a subscript, because delta H VAP is the molar enthalpy of vaporization, and that's what you use in the Clausius-Clapeyron equation. It also uses the gas constant R, which isn't any different than the ones you used in general chemistry for the ideal gas law. And T is the temperature of consideration, whereas T naught is the normal boiling point at 1 atmosphere of pressure. You use the temperature units that are appropriate to your delta H and your R. So it just depends on the units of each of these things as to which measurement you can, which unit you can use for each different variable. Now, some of you are going, well, wait a minute, because some of you may have had some of this, I don't know. But delta H varies with temperature too. So that's the problem with the Clausius-Clapeyron equation, is that there's, even though you're able to make an estimation with it, you still really can't make much of an estimation, because delta H also varies with temperature just a little bit, and it depends on what it is, because sometimes it's a significant difference. So we kind of have to fudge a little bit, and it turns out that it's generally okay for the purpose of working with some calculations to determine whether or not you can predict a fractional distillation curve. And I'll show you what I'm talking about in a moment. But what you have to do is pick the 2 components that you have in your mixture, or more. It could be more components. It depends on how many components there are. But you have to pick some partial pressures that you know from the literature, and you have to pick the temperatures they occur at. And then you have to find the normal boiling points. And you have to look at that, and you have to plug all of that in, and you arrive at a delta H that you can use for estimation. And what we do is we let that delta H that we calculate from this be constant for any other calculations we do with the equation. So it is a very broad estimation tool, but it turns out that it does predict pretty well the numbers we should see in some of the smaller fractional distillation setups that we're going to work with in our lab. So it can work in this way, but when you take further courses with this, you'll have to actually do some calculus to account for little changes that occur over time and over temperature differences in this equation. Alright, what this comes back to is the first set of equations we talked about. So if we know that the mole fractions of every compound add up to be 1, then we can rewrite the relationship of the combined Rayoult's law and Dalton's law relationship to be all in terms of a single mole fraction. And that lets us separate everything mathematically until we're left with a solving equation for the mole fraction itself. For a binary mixture, this process is pretty easy. For a non-binary mixture, there's going to be a lot more variables in here, and so those numbers could be harder to come to. You'd probably have to do some matrix algebra and set up some systems of equations to do it most efficiently. So the problems can become more complicated, but they're still solvable as long as you've got some values you can plug in and work with. Ultimately, though, if you're ever asked any question on a quiz or a test, it will be a question much like this one, where you have some pressures and you're asked to calculate the mole fraction in terms of a single component. And you should be able to do that much because it's a pretty simple equation. It's not overly difficult to use. So this is the only one I'm really interested in you actually learning out of all of this. But I want you to go through the rest because it will help you understand it'll help you understand what fractional distillation is really doing. Alright, so now is the big moment. We come to what is a theoretical plate. So, the reason they're called a theoretical plate is they're not something that you generally can reach out and touch. It's more of a mathematical concept. It's a math concept that explains what is going on inside a fractional distillation column and why it can separate things to extreme levels of purity, and you can have these large temperature jumps between things that may even be narrow together as you're collecting them, depending on how you want to look at it. And there's really two different ways you can look at a theoretical plate. You can look at it based on the plate height, which is given by the equations I have down here, or you can look at them visually by looking at a boundary for the boiling point of the two components being mixed together at given mole fractions and temperatures. And then you can look at the vapor temperature in relationship to the mole fractions. And those two separate graphs make a lower and an upper boundary, and between those two you have this space where the theoretical plates exist. Now, it depends on what mixture you start with as to how many you need to do the job. And you can do that graphically by, let's say I had a 50-50 mixture and I wanted to know how many theoretical plates I need to take one of the components to 100%. I go up to 50, then I go up to where the vapor temperature is in correlation to that. I go across, see my next vapor temperature, go up, go across. In this case, I would only need 2 plates based on the shape of my graph in order to do it. Oftentimes, it's more common to see 4 to 5 of the theoretical plates in a simple setup like the one we're using, where your column for your fractional distillation is about 30 centimeters in height. So that's one way of counting up the plates and looking at them and seeing that they're actual physical components. Then you have your method of looking at plate height. Plate height is where you take the length of a column and you divide it by the number of theoretical plates, and that gives you your theoretical plate height. Hopefully in a perfect world, your column would be 100% efficient, which means that every plate actually is the plate height that you calculate when you take the length of the column and divide it by the number of theoretical plates you should have. But in reality, you probably won't have a perfect fractional column. More than likely, you'll have something like a number about 10 to 20% greater or less than numbers you've had before, or maybe 10 or 20% less than the theoretical calculation of the plate height. And you'd have to take some experimental parameters to actually see what kind of plate efficiency you were getting. So we can't really calculate the actual plate height in this class. We'd have to do some more stuff to get there. And we won't approach that today, but we're just demonstrating that there is such a thing as an efficiency that comes in from having the theoretical number of the theoretical plates and then the actual number that you're able to obtain in the system. Now the bottom curve is generated from a combined Raoult's law being used for the normal boiling point and adding in substitutions of the Clausius-Clapeyron equation, and then the top part is more Dalton's law derived from variations on the ideal gas law with substitutions of the Clausius-Clapeyron equation. And that sort of delta H VAP component that's got the exponential multiplied in with it as well is what gives these two curves their kind of curvy looking shape. They're not very linear. They're kind of more curvy on the bottom, curvy on the top, and they have that nice inflection there, and that's because of that exponential term in combination with the heat of vaporization. Okay, so I threw this on here because some of you will want a different representation of what was going on with that graph that we talked about earlier. And if you look back at the graph with the theoretical plates that we drew in, this column here corresponds to theoretical plates at each level. So it shows you what's going on inside the column with relationship to this. And as you can see, it purifies the samples more as it goes towards the top of the column, and then they come over and they're condensed on the other side. And so essentially what that boils down to is that each of those lines, both of them, it doesn't matter which one you're talking about, are a set of ordered pairs going along generated from these functions where you have a point mole fraction and temperature. So mole fraction on the x-axis, temperature on the y-axis. And to get the bottom curve, we use the equation I've gotten right here, which essentially is that first law that we covered that I said everybody should be able to calculate that much. That is that's the mole fraction of the liquid, because you're looking at the vapor pressure for the normal boiling point. When you talk about that, it's all based on the partial pressures there. So it's the total pressure of the system minus the pressure from component B divided by the pressure of component A minus the pressure of component B when they were partial pressures for those compounds. Now, I told you before that the P in the Clausius-Clapeyron equation is the P naught in the combined Dalton-Raoult model. And that's true here too. So what's been replaced is the P naughts, because P naught is P, and P was equal to this expression, except that we added in some subscripts to demonstrate which temperatures we were talking about. So that's really the way all of that was plugged in, and it's a pretty simple substitution. It's just the partial pressure for B that's at the normal boiling temperature at 1 atmosphere multiplied by that exponential, where we have our delta H sub B that we're using, our gas constant, the temperature we're going to, and the normal boiling point for that component. And then we do the same for A down here, except we subtract what we had up here on the bottom to get that X sub A. And then we can plot the points if we have the data. The top line is a lot different, and rather than go through every bit of it, because I don't want to get too bogged down in the equations, This comes from the ideal gas law after you've rearranged it to account for the differences between total compositions down to the single composition. And what it boils down to is that the mole fraction of the vapor for the component A is equal to the mole fraction of the liquid for component A multiplied by the partial pressure of the pure component A at that temperature divided by the atmospheric pressure, which would be the atmospheric pressure for the normal boiling point, which would be either 1 atmosphere or 760 torricellis. We tend to use torricellis with this setup because we're talking about a 30 centimeter column here. I mean, it's not really big. You're talking about a small system. It's not a huge column. We're not going to measure things in pounds of square inches and pound foots and all these different English units you hear about for pressure. We're not using pascals. We're not using atmospheres or bars or any of that. Those pressures are too magnanimous for a simple system like this that's really small. We just won't quite reach those limits of pressure. It's going to be small measurements. That's why millimeters of mercury or torricellis work better. They're more reasonable. And basically what you do is you take this equation and you substitute the Clausius-Clapeyron equation into it just like you did for the other. And when you do that, you'll end up with basically the equation that you had over on the last slide multiplied by the Clausius-Clapeyron substitution for this pressure here. And then the only thing missing from this is that we're going to have to divide that result by 760 torricellis, or 1 atmosphere, depending on what the pressure has been measured in your other calculations. Okay, so I know that's a little bit long-winded, and I know that that it can be a little bit overwhelming for some people, but that's where all of these ordered pairs are coming from. That's where these graphs were generated, and you can do it for any 2 compounds as long as you have some of the data. And you could even write a MATLAB script to generate it all. And I tried to do that. It takes a little while, and I couldn't get it all to quite work out the way I wanted to put it into like an extra credit question, because you have to have some good kind of numbers to float into the matrices you want to use to do the calculations, so you get pretty close numbers. But I'm perfecting it, and we'll see if I can't do it soon. But anyway, we'll do that when we get there. Okay, so we're done talking about the equations. That is the general explanation that anybody could provide for how you can look at the boundaries in a fractional column and look at how many plates you have. And you can go up graphically and determine how many you need based on where you are on that mole fraction axis. You could also determine that probably using a system of equations, but I think that might be overly complicated. We have in the past had some questions on the quizzes where you look at the graph, like that I showed you, where you have the upper boundary and the bottom boundary, and you have the theoretical plates moving in the boundary, and you have some mole fraction that you're looking at for a particular compound, and you start at that particular concentration. I think I put one of these in the extra credit assignment that I've put up on iLearn, so you can play with it and kind of see how it works. And you follow up along and you determine how many theoretical plates you need for the separation. And you can also tell how many you could have in the column itself by going through it. So it'll be a good exercise for you to look at that, I think, and kind of see what you can come up with. Azeotropic compounds are essentially compounds that when they're in the mixture together, they both take on a constant boiling point as a mixture. And the best example of that that you'll find in any book is the classic one, which is ethanol and water. So when you're trying to separate ethanol and water, you can only get about 95 to 98% purity on a fractional distillation, because water stays trapped in the alcohol no matter what you do. You can't get that last 2 to 5% of water out. It just doesn't work without some extra additives. And so what you have to do when you have an azeotrope is you have to find a compound that azeotropes the compound you want separated from it better. And in most cases what they do is they use benzene for water, because water and benzene have this other azeotropic effect where the water wants to stay with the benzene. And it does. And you use this property for other kinds of things. For instance, when you do Fischer esterifications, under the presence of heat and acid, you generate water, and that water can cause the equilibrium to go backward and give you reagents instead of products. So what you do is you add some benzene when you're refluxing these things using a Diels-Alder trap, which is essentially kind of like those centrifuge tubes you all use in the lab with the tips, except it's a little bit bigger. You can fit it over a round bottom, and you can put a condenser on the top, and you can reflux it. And you can do that at a nice steady temperature where the temperature stays pretty constant in that system. And you can reflux it the whole night long if you want to, running the condenser on top, and it'll fall back down. And then what happens is that benzene pulls the water out, and it makes it stay in the Diels-Alder trap, and it goes all the way to the bottom. And you can take a pipette and you can remove it. So you can take the water out. And by taking the water out, you have forced the ester to go forward, and you don't get reagent backward from it as much. So you'll do some Fischer esterifications next semester, but you'll be using a very, very small setup, and you will not use any azeotropes to try to drive the water off, and you won't use any Diels-Alder traps and things like that. We don't do experiments with those with you all, to my knowledge. But they are fun to use. Now, vacuum distillation, I want to clarify, is distinct from rotovapping. They're two distinctly different things, but they're similar to one another in the sense that the rotovap is a modification of vacuum distillation. So a vacuum distillation, you can actually do that with a water aspirator, which is the device that you used last time when you used your Buchner funnels to vacuum filter the recrystallized products that you made. And your macro scale kit, and probably your micro scale kit too, has all of the things you would need to do it. You have an inlet, and on that inlet in your macro scale kit, I mentioned to several of you that that was a vacuum adapter, and that's exactly what it's for. You can hook flasks up to the distillation apparatus, leave the inlet in. You can actually put an ice bath underneath the flask that you're collecting your product in to keep it cold, so that it doesn't go back up into the system and you don't have any insensible losses in the system. And then you can hook a vacuum tubing to the inlet and hook it into the aspirator and turn it on, and it puts a pressurized vacuum on the system. And what that does is it helps lower the vapor pressure at which items boil, because you are reducing the atmospheric pressure in the system. And so what they tend to use vacuum distillation for is when you have compounds that are mixable within one another, dissolve each other, they have that 25 degrees Celsius gap between one another, so you can get adequate separation, because you typically don't use a fractionating column with the vacuum. You pick one or the other. But you can use this vacuum to separate compounds with those degree separations that have boiling points greater than 150 degrees Celsius at 1 atmospheric pressure. So you can basically reduce the time it would take to use all of that energy, because those thermo wells that, or those little mesh fiberglass rheostat-based thermo wells that you sometimes see in research labs that aren't the typical ceramic thermo wells that you all get to use, those don't reach temperatures much greater than 150 super easily. in a way that maintains it very well. So you want to try to conserve that energy, especially if you're trying to use something like a steam bath to get something off. You'd have to apply some vacuum, because as you no doubt remember, steam baths generally only give you about 100 to 120 degrees Celsius maximum temperature that you can achieve, and you have to keep it pretty close to the heat source in order to maintain that, because there's not a lot of insulation between the air and the steam bath itself. So it's a tricky situation when you try to do something like that, and to help produce the time and the energy, the vacuum helps. It really helps some things come off, because there's some stuff you just couldn't get to come on over, and other things you could. It just depends. It depends on what we're doing. Now, the difference between vacuum distillation and rotovapping is that generally all of these will be true, but it tends to be used more for rapid removal of solvents in order to concentrate solutions that have a product in it you want to either recrystallize or retrieve or do some extraction work with or something like that. And the rotovap is different in that it rotates, it spins. So generally, most rotovaps, you've got a water bath, you've got some water in it, you can heat up that water, you can increase the temperature, you can get it up to around 150, pretty good. Much beyond that, though, would be kind of hard to do without a lot of energy. But you could possibly come up with something like that. And then what's going on is you can angle most of them now, not all of them. It depends on how old they are, and some of them have mechanical parts and some of them are more automated. Most of them are automated now. But you can rotate that whole apparatus around and get the angle of that flask into the water bath. And then you have, in addition to that flask, you have what they call keck clips. They're little plastic clips that fit over the joints, and they make sure they don't fall off while something's spinning, or when you have it together in an apparatus. And some people actually use keck clips in any apparatus that they're setting up, because a lot of the newer organic glassware sets have these in them, and so you just set them up automatically whether you're doing something rotational or not. Not all sets have that, though, but they're pretty easily purchasable. They're fairly cheap. They're plastic. They're, you know, it's not really that expensive. But there's usually a trap that is put into, they call it the solvent trap, and what it is a flask that's in the middle between the main collection vessel and the reagent and solvent vessel that you're putting into the bath. And what it does is it traps solvent that tries to drip back down and go back into the flask, and that keeps the energy going into the bottom flask instead of trying to heat solvent that's falling back in and trying to repressurize it to go back up. You keep it in a separate flask and it keeps warm from the solvent that's coming back into the trap. It's really quite something. And then over time, all of that travels up into the column, and this column can be made of, it's usually made of a really high grade pressurizable glass, very thick walled, and a lot of the newer ones have a coil of glass tubing that goes inside the collection column, and it will have a cooler attached to it with hoses. So you can refrigerate water and run it through, and sometimes they even have commercial grade coolants that you could run through these if you want to cool it down even more, and you could do that. And it's usually like some kind, it looks like a computer tower, essentially. But it's a refrigerator is what it is. It's a refrigeration pump. And it's a refrigerating water pump. That's what it is. And so most of the time it's water. And you run it through. And while you're cooling it, you're also pulling a vacuum on it. So it's typically not the aspirator that you're using for that one. You use more of a commercial grade vacuum, which can get like up to 100 bar negative pressure when it's pulling a vacuum, sometimes more than that if you've got a really good one. But you want to be careful about the pressure. You have to stay within the safety ranges. But you can really pull a vacuum on this, and it will get a lot of solvent off. There's a nice big thick collection flask on it. It's the coolest thing. But the whole point of having one is the fact that it, A, can be vacuum, B, is condensed, and 3, it rotates. And the rotation is important because what that does is it allows the solvent to go over a wider surface area on the flask, and that lets more energy fuse through and, well, not fuse through, but flux through. It lets more energy flux through the solvent and allows it to evaporate faster. So it's cool to see. You can probably find some videos of it on YouTube. We won't get to use one in lab. There are research labs around in the building, and you may see one sitting there. They're very expensive instruments, so don't touch any of them unless you are working with one for real and are working with that person, because they're very expensive pieces of equipment. But they are also very important for synthetic work if you don't want to sit there and get your solvent out forever. As far as condensing goes, in your setups that we'll talk about, you have a standard column, and then you have a cold finger condenser. The same can go for rotovaps. They can have a cold finger, or they can have a coil. The coil lets water run through it. The cold finger, you can put ice in it, ice water, ice and salt to make it even colder, acetone liquid nitrogen slushes, CO2 in the form of dry ice mixed with acetone or other types of solvents depending on what you want to achieve. And all of those create different pressures, or not pressures, but different temperature ranges that you can lower the temperature to. Some of them get, maybe 20 degrees below zero. Some go 78 degrees below zero. Some go in between those, and sometimes it's 5 degrees Celsius. It just depends on what you're using. And you have to cater to the particular thing you're doing. As far as steam distillation is concerned, because I mentioned that it is a type of distillation that's special that you can use, predominantly it's used for separating tars, oils, and liquids that aren't very soluble together most of the time. Some of them are, but there's a phase in there that's not. So if it's something like water, which comes from steam as well, the compounds that you're distilling with it may not be soluble in it, or they may be very, very slightly soluble, but not extremely soluble. And so in those cases, steam distillation is used. The biggest place where you'll see this right now, that most of you can relate to, I think, is in the perfume and fragrance industry. Steam distillation is pretty big with essential oil and components from plant materials that they use in fragrance making, aromatherapy, different kinds of things, even food additives, really. And the whole process depends on acquiring a lot of plant material, generally more than just a little bit, because it takes a whole lot to get an appreciable amount of those compounds. And then you put them in a giant steam column. It's pretty big if you're going to do that much, use that much mass in it to make actual products with it. But you can do a small setup with quite a bit of material And this was actually done over the summer with a K-12 outreach project that chemical engineering was doing with Dr. Stretz, I believe it was. She had the female high school students doing orange oil distillations with water setup. So that applies to all of this. But that's the only time you'll probably see that, and we won't use any steam distillation in our lab. But I want to throw that in there because it is something that you sometimes see being used. It just depends on the project you're working on and what you might do with it. We'll talk about how to set up your different apparatuses next, and mostly I'm just going to show you the same diagrams that you all have in your books, but I am going to talk about some little areas I notice where students have a great difficulty keeping the apparatus together and it works against them for what they're doing, and so we'll talk about how to troubleshoot some of that. What we have here is the two different distillation setups that you'll use. So here's the simple on the left. We're using those lollipop thermometers that you check out from the stockroom. You'll be putting them through your thermometer adapter here on the top and securing those into this distilling joint that's in your macro scale kit with your round bottom. Then you hook your condenser up in the other joint, cap the joint, and then we clamp here and leave the space between the graduated cylinder and that joint open so that we don't close the system, because remember, we never heat a closed system. Also, little tips to remember: when you plug in your water, make sure that the water inline goes into the slanted bottom part of the column and flows to the top, to the drain. That's really important. We always want to work against gravity when we fill the column. It prevents turbulent flows inside the column and helps it do its job a little bit more controlled. And then for your fractional distillation, you'll use a different setup. Some of you will use the glass beads, others will use the steel wool that we have and pack it in here. Your column will go in there, your distilling joint there, thermometer adapter up here, and then you'll secure the same distilling joint you used here onto the distilling joint directly and put a cold finger condenser in where that stopper went in the other. And so your water in will go here on the top where it goes, which fills into the cavity. The cavity fills up and it drains out of the top into the drain, and that will condense the liquids on this cold finger right here. And again, we're not heating a closed system because this is open, so make sure that you do that correctly. You'll want to make sure that you support any of the structures that you have here with a ring underneath, possibly a screen if you have one to keep things nice and flat. So your heating mantle should always be supported in any of these apparatuses. You don't want anything too hanging off. And be careful that you don't put too much torque on any of the apparatus while you're putting it together, because you could break the glass and it could possibly injure you. So be careful of that. Now, one other thing to keep in mind, and I say this only because I notice it so often, and if I notice it, I'll point it out to you. But generally, you'll point it out to me before I notice it, because there are so many of you and I'm watching so many apparatuses at once. But in order for your distillation to work, you actually have to have a tight seal between all of your joints. So you can't have one partially open. A lot of times what happens is you accidentally bump the clamp just a little bit, and it pulls just a little bit on the condenser, and it opens up just a little tiny crack in this connection, and then your vapor escapes and your temperature starts to drop, and you all go, why is my temperature dropping? It was up and now it's down. And then I come over and I'm like, well, you need to fix this. And then when you do, it goes back up again, but you lost some of your product in the process because you were venting it into the atmosphere. So really watch those joints. And if something's not going or if it's staying stuck, then you need to come and get one of us because it may need some grease. We use a silicone-based lubricant on these joints, and they need to be clean, and sometimes we need to reapply the grease, but we do so sparingly. You don't want them too slippery either. That's pretty much it. As long as you follow those simple rules, your distillation apparatus should work effectively for you. It's a pretty simple apparatus. I think you all will have fun with this experiment, and I look forward to seeing you on Monday.